The primary difference between electronic circuits and classical electrical circuits is that electronic circuits provide a great deal more control in the amount and direction of flow of currents in various parts of the circuit. Diodes are one of the most basic components of electronic circuits which help us control the direction of the current. Ideally, diodes conduct current only in one direction, and the simplest application which comes to mind with such control is AC power to DC power. Right? This is the most commonly used symbol for the diode, with the cathode here and the anode here. You can see that the symbol is chosen to represent the direction in which the diode allows the current to flow. All the information we need to determine how a particular component behaves in a circuit, and therefore to analyze the circuit, is the component's IV characteristic. In IV characteristic, x-axis represents the voltage across the component, and the y-axis the current flowing through it. For an ideal diode, there should be no voltage drop in the forward direction, that is from the anode to the cathode, when it is conducting any amount of current. This is ideal because there is no power being dissipated in the diode when it is conducting. That means for any positive current, the voltage drop is 0. Therefore, the IV characteristic should include the entire positive y-axis. On the other hand, when you apply any amount of voltage in the reverse direction, from the cathode to the anode, there should be no current flowing through the diode. Therefore, the IV characteristic should include the entire negative x-axis. Now let's see how real diodes behave. This is a typical IV characteristics for a real diode. In the forward direction, the current is given by this formula. In the reverse direction, there is a very small reverse current, also called saturation current or scale current, until the reverse voltage reaches the breakdown voltage, also known as Zener voltage. Note that having the diode in the breakdown region doesn't necessarily mean that the diode will be damaged. As long as it can handle the heat being generated, it should behave normally when the reverse voltage is reduced. Also, this is not necessarily a bad thing, as we will see in the next video, that we can take advantage of this breakdown in useful applications such as voltage regulation. Once the reverse voltage reaches the breakdown voltage, the diode starts conducting, and very small increases in the reverse voltage can lead to large increases in the reverse current. This slope in the reverse direction is usually steeper than that in the forward direction, which makes this region more suitable for voltage regulation. As you can see, there is a range of voltages where the real diode behaves almost like an ideal diode. As long as the reverse current before breakdown is small, we can ignore it for all practical purposes. And as long as the forward voltage before the diode starts conducting any reasonable amount of current is small, it is again close to an ideal diode. Since the exact IV characteristics of diodes is very nonlinear, it is difficult to use in analysis. We will now look at some approximations we can make to ease our analysis. In the following, we are only interested in the forward direction. The first is, of course, replacing the real characteristics with an ideal one. This is a good approximation when all other voltages are much higher than the forward conducting voltage, which is typically about 0.7 volts for a PN junction diode. Second, we can use the constant voltage drop model with the current 0 until the forward voltage reaches a certain value and could be any current at that voltage. If that does not provide accurate approximation, we use this piecewise linear model. If all above approximations fail to provide reasonable approximations, we can resort to using the exact model with numerical methods, which is what most simulators do. Of course, choosing the right model for a given analysis is a judgment call. And when you have easy access to simulator, it makes that choice a bit simpler. The above approximate models can also be very useful in designing circuits, as they provide an easier way to think about how a diode behaves in a circuit. There is another interesting and useful linear approximation of diode operation. Consider a situation where there are small variations in voltage across the diode, and we are interested in computing the variations in the current through it. Note that we can approximate any curve in a small neighborhood around a point reasonably well with its tangent at that point, provided the neighborhood is sufficiently small. Therefore, we can separate the DC and AC analysis by creating a small signal model for the diode. Since we're making a linear approximation, the small signal model is just a resistor. But since the tangent changes from point to point for a nonlinear curve, the value of that resistance changes with a DC current. To summarize, in this video, we saw how an ideal diode should behave like, the IV characteristics of real diodes, and various approximate models we can use. In the next video, we will look at some applications.